Space is cold enough to make your blood freeze solid in seconds. That is what almost everyone believes. It is also completely wrong. If you were ejected into the vacuum of intergalactic space right now, freezing would not be your first problem, your second problem, or even your 10th problem. You would be dead from something else entirely long before the cold ever got the chance to touch you. The popular image, ice crystals forming on your eyelashes within a heartbeat, your whole body seizing up like a statue in a blizzard, is basically science fiction. And the real answer is slower, stranger, and honestly a lot more disturbing. So today we are asking a very specific, very morbid question. How fast would you actually freeze in the emptiest, coldest place the universe has to offer? The vast nothing between galaxies, a region so empty, it makes the vacuum around the International Space Station look crowded by comparison. And to answer it properly, we have to walk through exactly how a human body loses heat, why the void breaks almost every rule your body is used to, what would actually kill you first, and what happens when you drag that freezing process out across the single coldest environment physics allows. Let's start with the basic physics of staying warm, because it is stranger than you think. Here on Earth, your body loses heat three ways. Conduction, which is heat draining into something you are touching, like cold water or a metal railing. Convection, which is heat getting carried away by moving air or fluid, like a breeze on a winter day. And radiation, which is heat leaving your body as invisible infrared light, the same way a campfire radiates warmth even if you are not touching it. On Earth, conduction and convection do almost all the work. Air molecules bump against your skin constantly, stealing warmth and carrying it away. But space is a vacuum. There is essentially no air, no water, nothing to conduct or convect through. In the emptiness between galaxies, the average density is roughly 1 atom per cubic meter, which is so close to nothing that for practical purposes it is nothing. That means 2 of your 3 heat loss mechanisms simply switch off. The only one left is radiation, and radiation, it turns out, is slow, painfully, unglamorously slow. To understand just how slow, we need to bring in a formula named after 2 19th century physicists, Joseph Stefan and Ludwig Boltzmann. The Stefan-Boltzmann law tells us that the rate an object radiates heat depends on its temperature raised to the 4th power. That 4th power detail matters enormously. It means a hot object radiates heat away quickly at first, but as it cools, the rate drops off fast, because you are no longer multiplying by that huge exponent. Your body sits at roughly 310 Kelvin, a comfortable 37 degrees Celsius, using your skin's surface area and its emissivity, which is close to 0. 98, meaning your skin behaves almost like a perfect radiator. Physiologists have actually modeled how long an exposed human body would take to radiate away enough heat to freeze solid in a vacuum. The answer is not seconds. It is not minutes. It is closer to 12 hours. 12 hours of losing warmth into the void before your tissues would actually reach a fully frozen state. Compare that to the popular image of an astronaut turning into a human popsicle within moments of losing their suit, and you can see just how wrong Hollywood has gotten this one. Films love the instant freeze because it is visually dramatic and easy to explain in a single shot, but the real physics is almost the opposite kind of story. A slow, quiet, radiative bleed of warmth stretched out over the better part of a day. Not a violent flash freeze anyone would notice happening in real time. But here is the twist nobody expects, and it is the reason your body would never actually get the chance to freeze in the first place. Long before the cold becomes the threat, the vacuum itself kills you through an entirely different mechanism. In 1965, a NASA test subject named Jim LeBlanc was testing a spacesuit prototype inside a vacuum chamber at the Johnson Space Center when his suit sprang a leak and depressurized. Within roughly 14 seconds, he lost consciousness, not from cold, but from the rapid drop in pressure pulling oxygen out of his blood and lungs. He survived, thanks to a quick-thinking colleague who repressurized the chamber, and he later described the strange sensation of his saliva boiling on his tongue in the instant before he blacked out. That detail sounds bizarre until you understand basic chemistry. In a vacuum, the boiling point of a liquid drops dramatically, because boiling is simply the point where a liquid's vapor pressure matches the pressure around it. Remove the pressure entirely, and liquids can boil at body temperature instead of 100 degrees Celsius. So the grim reality of unprotected exposure to space is not freezing. It is a condition called ebullition, where the water in your soft tissues and blood vessels begins to vaporize. Your body swells grotesquely as gas expands beneath your skin, and within about 10 to 15 seconds, you lose consciousness from lack of oxygen. Death typically follows within 1 to 2 minutes if nothing is done to restore pressure and oxygen. That is your real timeline in raw vacuum. Not a slow, cinematic freeze, but a fast, brutal asphyxiation with your saliva and the moisture on your eyes actively boiling away in the same breath that your body is technically capable of freezing. The LeBlanc incident was survivable because it lasted only seconds and help was standing right there. History has a far darker example of what happens when it is not. In June of 1971, the crew of Soyuz 11, cosmonauts Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev, were returning to Earth after a record-setting stay aboard the Salyut 1 space station when a valve in their capsule jolted open during the separation sequence, venting their cabin's air into the vacuum of space. Within about 30 seconds, their capsule had fully depressurized. All 3 men died from asphyxiation before rescue teams ever reached them, and to this day, they remain the only humans known to have died in the vacuum of space itself, rather than during launch or re-entry. Post-mission analysis showed signs consistent with embolism and rapid oxygen loss, not cold exposure. Their deaths are part of why every modern spacesuit and every capsule design since has been engineered with redundant seals and pressure sensors, because the lesson from Soyuz 11 was brutally clear. In the vacuum of space, the clock that matters is measured in seconds, and it has nothing to do with temperature. Now, before we go further out, and things get genuinely stranger, if you are the kind of person who likes having their assumptions about the universe quietly dismantled, this channel exists entirely for that feeling. So consider subscribing, because we are just getting started. And what comes next is significantly colder, significantly darker, and significantly further from any hope of rescue. So if we are going to answer the original question honestly, we have to change the rules of the experiment. Let's imagine, purely as a thought exercise, that something protects you from the vacuum itself, some kind of sealed, pressurized, life support pod with a clear viewport. So the only variable left is temperature. Now we can actually watch the freezing process unfold properly, stage by stage, as we push further and further from any source of warmth. It helps to understand what freezing actually does to a human body before we start dragging you across the universe. Your body is roughly 60% pure water by weight, and when that water gets cold enough, it does not turn to ice smoothly and gently. It forms sharp, jagged ice crystals inside and between your individual cells. Those crystals act like tiny knives, physically rupturing cell membranes from the inside out, which is why frostbite damage is often permanent even after rewarming. The structural damage to the tissue has already happened. Your body would not freeze evenly either. Extremities go first: fingers, toes, ears, nose, the parts of you with the least blood flow and the most surface area exposed relative to their size, which is exactly the same reason frostbite claims fingers and toes on Earth's coldest mountains and polar expeditions long before it ever touches your core. Your body's circulatory system would actually fight this process for a while, a reflex called vasoconstriction, where blood vessels near your skin clamp down and reroute blood toward your vital organs, sacrificing your extremities to protect your heart, lungs, and brain for as long as possible. It is the same reflex mountaineers on Everest's death zone rely on, and the same reflex that eventually fails when the cold becomes overwhelming and unrelenting, which, out here, it always eventually does. Your body is, in a very real sense, built by evolution to fight the cold of an ice age on Earth, not the absolute, patient cold of the space between galaxies. And eventually, every biological trick it has runs out of road entirely. Let's start close to home. Low Earth orbit, roughly 400 kilometers up, is deceptively temperate as far as space goes. In direct sunlight, surfaces can heat up to over 120 degrees Celsius, hot enough to boil water instantly. But duck into Earth's shadow, and temperatures can plunge to negative 100 degrees Celsius within minutes. Astronauts on spacewalks experience this exact swing, 16 sunrises and sunsets a day. Their suits cycling between blistering heat and brutal cold every 45 minutes. It sounds terrifying, but the suits are engineered with multiple insulating layers precisely because that thermal whiplash is real and constant. In our protected pod scenario, you would feel the temperature outside swing wildly depending on whether the sun's light is reaching you directly, reflecting off Earth, or blocked entirely. This is not the deep, ultimate cold of space. Earth's warmth and the sun's proximity are still doing real work to keep the environment survivable. There would also be something eerie happening the entire time, something almost no movie ever quite captures correctly, despite how many space films exist. Silence. Total, complete, absolute silence. Sound needs a physical medium to travel through: air, water, something with molecules close enough together to bump into each other and carry a vibration along. Vacuum has none of that, so no matter how violently your pod might shudder from a micrometeorite impact, or how loudly an alarm might blare inside your own sealed capsule, the void outside your window would transmit nothing at all. You would be watching Earth's blue curve slide slowly past your windshield in complete, suffocating quiet, broken only by the sound of your own breathing and the faint hum of your own equipment. It is a detail astronauts consistently describe as one of the strangest parts of spaceflight, more unsettling in some ways than the cold itself. Now push out past the moon, into interplanetary space, and the sun becomes your only real heat source, since Earth's glow no longer reaches you. The intensity of sunlight follows an inverse square law, meaning it weakens with the square of your distance from the sun. By the time you reach Mars, sunlight carries only about 43% of the energy it has at Earth. By Jupiter, it has dropped to about 4%. By the time a spacecraft reaches Pluto, sunlight is roughly 1,500 times weaker than it is here, and surface temperatures on Pluto hover around -230 degrees Celsius. This is roughly the environment New Horizons experienced on its historic 2015 flyby. A spacecraft engineer had to plan for temperatures barely 40 degrees above absolute zero. Push further out to interstellar space, past the outer edge of the sun's influence called the heliopause, which Voyager 1 famously crossed back in 2012 according to NASA, and sunlight becomes so faint, it is essentially irrelevant to your survival. You are now genuinely alone with only starlight from distant stars for company, and starlight, spread across trillions of kilometers, provides essentially no warmth at all. This is roughly where Voyager 1 itself lives today, over 24 billion kilometers from Earth and still transmitting, an engineering achievement that only works because its designers accounted for exactly this problem back in the 1970s. Voyager's plutonium-powered generator does not just supply electricity, it also generates waste heat that engineers deliberately channel to keep the spacecraft's electronics from dropping below their minimum operating temperature. Without that constant trickle of radioactive warmth, Voyager's instruments would have frozen and failed decades ago. It is a small, human-built rebellion against exactly the kind of cold we are describing, a tiny nuclear campfire keeping a machine alive in a place that wants nothing more than to erase all warmth entirely. If Voyager's generator ever fully depletes, which engineers expect sometime in the 2030s, the spacecraft will finally, fully, and permanently go cold, matching the temperature of the void around it for the rest of its existence. Now we leave the galaxy entirely, push beyond the Milky Way's roughly 100,000 light-year disk, past its faint stellar halo, and out into true intergalactic space, the vast gulf between galaxies that can stretch for millions of light years. Out here, there are no nearby stars radiating warmth, no planets reflecting sunlight, nothing but the occasional rogue photon that has been traveling uninterrupted since before Earth existed. The only meaningful heat source left in this entire region of the universe is something so faint most people have never heard of it: the cosmic microwave background. Discovered almost by accident in 1965 by Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs in New Jersey. The cosmic microwave background is the leftover afterglow of the Big Bang itself, radiation that has been cooling and stretching for roughly 13.8 billion years. Penzias and Wilson were not even looking for it. They were trying to use a large horn-shaped antenna for radio astronomy and kept picking up a faint, steady hiss of background noise they could not get rid of, no matter which direction they pointed the instrument. They cleaned out pigeon droppings from the antenna, they checked every wire and connection twice, and the hiss simply would not go away. It took a conversation with physicists at nearby Princeton University, who happened to be independently theorizing about exactly this kind of leftover radiation from the Big Bang, for Penzias and Wilson to realize what they had actually found. They had accidentally detected the oldest light in the observable universe, a discovery that earned them the Nobel Prize in Physics in 1978, and confirmed the Big Bang theory in a way no one had managed before. Today, it sits at a near-uniform temperature of about 2.7 Kelvin, which is -270.45 degrees Celsius. That is the temperature floor of the observable universe. It is not absolute zero, but it is close enough that for a human body, it is functionally the same as being wrapped in nothing at all. So here is the actual answer to our original question. Once you strip away the vacuum, the embolism, and everything that would kill you faster than cold ever could, in protected, insulated conditions, exposed only to intergalactic radiative cooling toward that 2.7 Kelvin background, a human body would take not hours, but potentially days to weeks to fully equalize with its surroundings, because the fourth power relationship in the Stefan-Boltzmann law means that as your body cools, the rate of further cooling drops off dramatically. The first stretch of cooling happens relatively fast, your body radiating away its 290-degree Kelvin surplus over Earth's ambient temperature in the initial hours. But the final stretch, closing that last gap between a merely frozen body and true equilibrium with the near absolute zero of intergalactic space, could stretch out asymptotically, technically never quite finishing, the same way you can keep having the distance to a wall forever without ever quite touching it. In practice, for anything we would call frozen solid, biologically finished, cellular structure destroyed by ice crystal formation, you are looking at somewhere between 12 and 24 hours if we are generous about what protection remains, dramatically longer if any insulation survives at all. Now, here is where the story gets genuinely dark, because the true horror of intergalactic space is not the freezing itself, it is the isolation that comes with it. Between galaxies, you are not just cold, you are farther from another living thing than any human has ever been or will likely ever be. The nearest large galaxy to our own, Andromeda, sits 2.5 million light-years away. If you were drifting exactly halfway between the Milky Way and Andromeda, the light from either galaxy reaching your eyes would have left over 1 million years ago. There would be no rescue, no signal, no possibility of return, only the slow, silent radiation of your own warmth, leading out into a universe that has nowhere else for it to go. Astrophysicists sometimes describe intergalactic space using an analogy about scale. If galaxies were cities, intergalactic space would be the empty ocean between continents, so vast that the overwhelming majority of the observable universe's volume is technically this kind of void. We tend to picture the universe as full of stars and galaxies, dazzling and crowded. But by volume, the universe is overwhelmingly emptiness, and you, in this thought experiment, would be sitting directly inside the most representative sample of what the universe actually is. Consider that our own Milky Way, along with Andromeda and a few dozen smaller neighbors, forms what astronomers call the local group, a modest cluster of galaxies loosely bound together by gravity, drifting through the emptiness together like a small raft of light in an otherwise black ocean. Zoom out further, and the local group is itself just one small piece of the Virgo supercluster, spanning roughly 110 million light-years. And even that supercluster is only a minor thread in an even larger structure called the Laniakea supercluster, mapped out in careful detail for the first time back in 2014 by astronomer Brent Tully and his research colleagues. Between all of these vast structures lie cosmic voids, regions so empty of galaxies that some stretch for hundreds of millions of light-years across, with the largest known examples dwarfing every supercluster combined many times over. Drift into the heart of one of those voids, and you are about as far from another living star as it is physically possible to be anywhere within the observable universe. Let's push the scenario to its absolute extreme, because 7 Kelvin is not actually the coldest the universe will ever get. The cosmic microwave background itself is cooling, slowly, as the universe expands. Right now, the universe is roughly 13.8 billion years old, and that background temperature has already dropped from thousands of degrees at the Big Bang down to a few degrees above absolute zero. But the expansion of the universe is not slowing down. It is accelerating, driven by whatever mysterious force cosmologists call dark energy, first confirmed through observations of distant supernovae in 1998 by teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees, work that later earned them the Nobel Prize in Physics. As the universe keeps expanding, the cosmic microwave background keeps cooling and stretching further, and trillions of years from now, it will asymptotically approach true absolute zero, a temperature that thermodynamics tells us can never technically be reached, only approached forever. Physicists call the far future scenario tied to this process heat death, a state where every last pocket of usable energy in the universe has spread out and equalized. Long before that final state, though, there is an entire intermediate era worth imagining. Roughly 100 trillion years from now, the last red dwarf stars, the small, slow-burning stars that outlast every other type by a colossal margin, will finally exhaust their hydrogen and go dark, leaving the universe with no active starlight anywhere at all. What remains are the cooling embers, white dwarfs, and neutron stars slowly radiating away their leftover heat over unimaginable stretches of time, eventually cooling into cold, dark spheres called black dwarfs, objects so patient that not a single one is expected to exist yet in our current 13.8 billion-year-old universe, because it takes far longer than that just to form the first one. Even matter itself may not be permanent. Certain grand unified theories in particle physics predict that protons, the building blocks of atomic nuclei, are not perfectly stable and might decay over timescales estimated at 10 to the power of 34 years or longer, a number so large it makes the current age of the universe look like a single tick of a clock. If that prediction holds, then eventually even the black dwarfs and neutron stars themselves would slowly dissolve, atom by atom, into radiation and subatomic particles, leaving behind nothing but photons, stray electrons, and the faint, patient pull of gravity holding on to whatever mass remains. And even black holes eventually evaporate through a slow quantum process called Hawking radiation, first proposed by Stephen Hawking in 1974, over timescales so vast that a supermassive black hole might take 10 to the power of 100 years to fully vanish. Imagine drifting, protected and functionally immortal for the sake of this thought experiment, into that unimaginably distant future, long after every star has burned out. Every galaxy has drifted so far apart from every other that none are visible from any other, and even the last black holes have quietly popped out of existence in a final flash of radiation. This is what physicists sometimes call the dark era of the universe, a period so vastly long that our current 13.8 billion-year-old cosmos is essentially the very first instant of it. In that far future, the ambient temperature would be closer to absolute zero than anything experienced by any object in this current era of the universe. Colder than the current intergalactic void by a staggering margin. Colder than anything humans have ever built or measured. Even colder than the coldest artificial temperature ever achieved on Earth. Roughly 100 picokelvin. Produced by physicists at Aalto University in Finland, cooling a nuclear spin system. Freezing there would not take hours or days. It would happen in an environment already so profoundly cold that the concept of freezing almost stops meaning anything, because there would be no meaningful difference left between something frozen and the near-vacuum silence surrounding it. And this is where the thought experiment turns genuinely philosophical, because some physicists, including Roger Penrose in his work on conformal cyclic cosmology, have speculated about what, if anything, comes after a universe cools this completely. In an environment with no particles left to interact, no clocks left to measure duration, some theorists argue that time itself effectively loses meaning, that a maximally cold, maximally empty universe might, in a strange geometric sense, resemble the hot, dense conditions of a new Big Bang, simply viewed at a radically different scale. It is a controversial and largely unproven idea, but it captures something true about how physicists think about cold. Cold is not just the absence of heat. It is the state that everything in the universe is very slowly, very patiently drifting toward, one radiated photon at a time. And the void between galaxies you would be sitting in during this thought experiment is not some exotic anomaly. It is the universe's default setting, the destination everything else is on its way to, given enough time. So let's bring this back down to something human. Right now, on Earth, you are surrounded by roughly 10 to the 25th molecules of air in every breath, constantly stealing and returning warmth through conduction and convection, keeping your body locked at that comfortable 310 Kelvin without you ever having to think about it. That warmth is not a given. It is an extraordinary local exception in a universe whose overwhelming default is silence, emptiness, and cold that never technically finishes arriving. Every star that has ever burned, every planet that has ever held liquid water, every warm-blooded creature that has ever existed has been a brief, localized rebellion against the void's slow, patient pull toward equilibrium. When you think about it that way, the fact that you are sitting somewhere warm enough to read this, breathing air dense enough to carry sound, orbiting a star still young enough to burn for billions more years, starts to feel less like a mundane fact of life and more like a genuinely rare cosmic accident. Think about the actual numbers for a moment. Our sun is roughly 4.5 billion years old, and it has perhaps another 5 billion years of stable hydrogen burning left before it swells into a red giant and makes Earth uninhabitable. That gives complex, warm-blooded life on this planet a total viable window measured in mere billions of years. A blink compared to the 100-trillion-year lifespan of the smallest red dwarfs, and an even smaller blink compared to the near-infinite stretch of cold, dark eras that follow. We are not living in the universe's typical conditions. We are living in an exceptionally narrow, exceptionally brief, exceptionally lucky slice of cosmic history, early enough that stars are still forming, still burning, still radiating enough concentrated warmth to make liquid water and layered atmospheres and functioning biology possible at all. Most of the universe's history, by a staggering margin, will be spent in conditions closer to the void we have been describing than to the comfortable, sunlit world you are sitting in right now. Maybe that is the real answer to how fast you would freeze out there. Not a number of hours or days, but a reminder that everywhere else in the universe, given enough time, eventually does. Earth is the exception, not the rule. And every second you spend warm is borrowed against a universe that is, very slowly, trying to take it back. Every sunrise you have ever watched, every warm breeze you have ever felt on your skin, every ordinary Tuesday you barely noticed, happened inside a window of cosmic time so narrow that most of existence will never get to experience anything like it at all. That is worth sitting with for a moment, not as something frightening, but as something quietly remarkable, a kind of cosmic privilege most matter in the universe will never get the chance to enjoy. But there is another question hiding underneath this one. A stranger question about what happens to information, to memory, to everything that ever mattered to anyone. Once the last warmth finally bleeds away into that patient, waiting cold. That is a story for another What If.